Okay guys, this is the most important lecture of the whole unit. This one and the next one. So I'm going to ask you to pay very close attention. It doesn't matter how much you listen to me. If you do not practice, okay, it's not going to help you. So I need for you right now, pause the video, go get your packet on buffers, and then get your calculator ready. You are solving those problems with me. Okay? Just watching me, listening to me, it's not going to do you any good. You need to practice with me. So this is chapter 17.1 and 17.3 in your textbook. It is the common ion effect, buffer, acid-base titration. So I may be done with buffers today and then continue with acid-base titration next class. Objectives. We will be able to predict qualitatively and calculate quantitatively the effect of an added common ion on the pH of an aqueous solution of a weak acid and a weak base. We will describe how a buffer solution of a particular pH is made and how it operates to control pH. You have learned since last year a buffer is a substance that resists a change in pH. Why don't you pull out your agenda book, write down your homework. You need to do Quest Acid Base Chemistry number 5. We are at number 5. Alright? And then you have your lab. Your pre-lab is also due. Quest number 5. Again, we had solved a problem like that last unit. Let's do one with this unit, the common ion effect. It says the extent of ionization of a weak electrolyte is decreased by adding to the solution a strong electrolyte that has an ion in common with the weak electrolyte. So let's do an example. So calculators, what is the hydrogen ion concentration? They ask you for hydrogen ion concentration of A. They give you the concentration of HF solution dissolved in 0.2 molar sodium fluoride. They gave you the Ka for HF. Ka for HF. Now, let me tell you the most common mistakes you make here. They see two substances, they see HF dissolved in NaF, and they have tendency to do HF plus NaF. Do not add those two together. Let me tell you how you know what to add those two substances. This is a weak acid. This is a salt. This is a soluble salt. We will end up with F minus. This is a weak acid and it's conjugate base. Weak acid and conjugate base, that's what form a buffer. So you should never ever put the weak acid or the weak base when it's with its conjugate on the same side. So let me reset this. So remember, this is a no. Reset. Now what I need to do is I need to write an equilibrium with my weak acid. This is HF. Equilibrium, this is a weak acid. Give me H plus F minus. Now that's salt. This is NaF is a soluble salt. It will dissociate completely into Na plus and F minus. So if I start with 0.20 molar and 0.20 molar NaF, I will end up with 0.20 molar Na plus and 0.20 molar F minus. Since this is the conjugate of a strong base, it is a spectator. I don't care about it. It is neutral. So what I care about is the F minus. What is the F minus? It is a common ion to this equilibrium. So if I make this is a weak acid, I will make my rise table. My rise table initial for my HF is 0.05. My initial for H plus is 0. My initial for F minus is not 0. It is 0.20. Okay, this is my minus X. This is plus X. So my E is 0.05 minus X. This is minus X plus X. You are right. Plus X. This is 0.20 plus X. And I write my expression. It is 6.8. It is my Ka. Now, yes, it is an acid. It is an acid. The equation. Always pay attention. So this is 6.8. My expression. Let me write the expression first. This is Ka equal the concentration of my H plus time the concentration of my F minus over the concentration of my HF. Therefore, my Ka, which is 6.8 times 10 to the negative 4 equal my H plus, this is X. So get those calculators ready for me, please. Can I have, like always, let's do the girls neglect X, and then the boys, let's do it don't neglect, okay, to save time. So this is my X times, this is 0.20 plus X, and then when I say neglect, it's both ways. It's not just on one. You can neglect this one also. Everywhere you have plus X or minus X, just neglect. On the bottom, I have my HF, which is 0.05 minus X. Okay, so the girls, let's neglect this. Okay, neglect. Let's neglect. Okay, so let's solve for X equal. Okay, who has X? Okay, X equal 1 point what? 6 times 10 to the negative 4. 1.7. Okay, 1.7. Who has something different? You have the same thing. Okay, so we can neglect 1.7. Very good. But remember what they asked for. That's what they asked for. Is that right? Okay, now what I need for you to understand, you can use Le Chatelier's principle to explain exactly what's going on. If you did not use any salt, if you did not use any F minus, all right, so you would have if you did not use it, then you would have more H plus. Because you have F minus, you add F minus, is going to shift this equation to the left, make less HF to less HF will dissociate. Okay, so I need for you to do it, to see it as math, also see it as in theory. Le Chatelier's principle will shift it to the left, make less HF will dissociate. Therefore, your H plus is less when you add that, when you have that common ion. All right. I'm going to come back to this and show you something. I just thought of this. I didn't think of it, but I will come back to that. Now, this is your favorite pot, buffer. So you already know. From last year we said buffer, so solutions of a weak acid or a weak base with its conjugate. Remember that conjugate usually, almost always, will be a salt. I just show you that NaF will dissociate into Na plus and F minus. That F minus was the conjugate base of HF. So you can say they are solutions of a weak acid or a weak base and its conjugate or its salt, because that conjugate will be a salt. Alright, how does the buffer work to resist a change in pH? When we say resist a change in pH, it does not mean the pH won't change at all. It will change a little bit. A little bit. So what happened? If you have a weak acid and its conjugate, which will come in the lab as a salt, weak acid and its conjugate, you come and add a strong base to that solution. That means you are adding OH minus. The HF, which is the acidic part of that buffer, will react with the OH minus, and then you are decreasing the HF. OH minus react with HF, you have less HF, you are increasing the F minus, but you did not really affect OH minus or H plus, because that's what makes the solution acidic or basic. Alright, you have that conjugate, the weak acid and its conjugate, you come and add an acid, you add H plus. Okay, you add H plus. What happened that H plus, which is the acidic part, will react with the conjugate base with the F minus to produce HF. You are increasing that HF, you are using up the F minus. So you have the weak and its conjugate, whatever you add, it will, one part of that mixture will react with it. That's what makes it resistant to a change in pH. I hope you understand what's going on. Now, listen carefully. This is the favorite part. When you look at your book will use pages to solve one buffer problem. Okay? They will use 2, 3 rice tables for one problem. And then they come up with an equation called the Henderson-Hasselbalch equation. Short HH equation. They say this is a short way. But I have good news for you. We are not using all of those pages. We are not even using the HH equation from the book. So, that's why you need to pay attention, because we are not using what you will hear in lectures from colleges. We are not using what you have in your textbook. The one and only formula we will use, as long as you have a buffer, is this formula. Nothing else, nothing more, nothing less. All you have to know is recognize you have a buffer. If you have a buffer, doesn't matter what they ask. If they ask for pH, use it. If they ask for pOH, use it. If they ask for H plus, use it. If they give you KB, don't use KB, use Ka. Whatever they give you, I need for you to use this formula. Okay, H plus, concentration of H plus equal Ka over the acid over the base. Don't try to change it because they ask you for OH minus. Don't try to change it because they give you KB. No matter what, I need for you to use this formula. Let's see how we can use it. Calculate the pH. They ask you for pH of a 0.5 molar. At least they tell me it is a buffer solution. I don't have to think. They tell me it is a buffer solution. Composed of, they give me the molarity, and then this is ick. That means it is an acid, and it's an acid. And then they give me the molarity of what? They give me something formate, 8. Sodium formate. I know it is the salt. Before, they asked me to calculate the pH before, and they asked me to calculate the pH after. The 10 ml, the complicated things here, they are adding different, we have different volumes. and then they are adding a strong acid to that buffer, and they give me the Ka for formic acid. Ka formic acid. As long as I realize it is a buffer, the first thing I will do, I will write my buffer formula, nothing else. Okay, so I write down the buffer formula, which is concentration of H plus equal Ka, doesn't matter what, Ka times, this is my acid, it is weak acid, it is weak acid over weak base. I write down my formula. Therefore, the HH plus equal, they gave me Ka. Ka is 1.8 times 10 to the negative 4 times concentration of my HA. My concentration of my HA, it is ic acid, it is 0.5. 0.5 over the concentration of my base. This is my base. It is the conjugate base of that weak acid. It is 0.70. Okay, therefore H plus equal 1.29 times 10 to the negative 4. Okay, 1.29 times 10 to the negative 4, but it's not what they asked me for. They asked me for pH. Therefore, pH equal, what is the pH? Say that again. 3.89. Thank you very much. It is 3.89. Okay? So we have a weak acid and its conjugate base. You have a pH of 3.89. Now, this is not too bad, but they come and add. They add hydrochloric acid to that buffer. This is what you do. Don't panic. Don't panic. Everything will be okay. This is what we will do. Let me reset. And I get my page. I have a buffer. It doesn't matter what they do to it. I'm going to write the formula for my buffer. Nothing else. This is H plus equal Ka times, this is my weak acid, over my weak base. But the problem, they add a strong acid to it. When they come and add to your buffer, this is what you do. If they add an acid, I'm going to put plus. I'm going to put my acid here. And I'm going to take away that same amount of acid from the base. Because what happened, that acid will react with the base and produce that conjugate. That acid will react with the base. I'm using up my base. It's producing more of that weak acid. I'm adding to the acid. So whatever I take away from my base, I'm adding to the acid. But here's the trick here. And listen to me carefully. Whenever you start adding to your buffer, I need for you to use moles here, not molarity. Let me tell you why. You don't want, we are here to help you make things easier, not harder. The reason why you have to go to moles, remember you are adding volumes to whatever you have here. You are diluting. You are changing the concentration. You would have to do a M1 V1 equal M2 V2. Find a new concentration for each one of them. You don't want to get into this. So the easiest way is to make sure you always go to moles whenever you are adding something to your buffer. And to make it even easier, if it's already milliliter, you can use millimoles. You don't have to go to moles. Okay, so let's take that bracket off. Okay, let's get rid of that bracket. We are going to use moles, so we don't have to worry about any volume. So what is the moles? Calculators, please. What is the moles of the weak acid? 0.25. Okay, this is 0.25, and this is millimoles. Is that right? It is moles. Okay, it is moles. Okay, what is the moles of the conjugate base? 0.35, 0.35, and this is moles. All you have to do, let me change the color. Why don't we add moles? Remember, this is acid. Is that right? We are adding the acid, the moles of the acid to the acid. So we have to be careful here. Because you use moles, let's put this in moles also. 0.01, 0.01. And then we are taking away the exact same amount to the base. Okay? So equal. Why don't we do this first? What is this? Yes. This is 0.26. And then do this one. Okay? And then do the whole math for me, please. (1.38 times 10 to the negative 4 molar). And they ask me for pH. pH equal what? 3.86. Do you remember what the pH was before we add that strong acid? 3.89. It changed it a little bit. Even though you add a strong acid, it was 3.89. You add, and look at this, you add 1 molar, 10 ml, 1 molar strong acid. The pH just went from 386, 389 to 386, which is nothing. All right? So this is buffer. Let's do more. Okay, did we miss one? Yes, we did. Oh, wow. I think we will go a little bit longer this time because we need to do more. If it's the exact same thing, I won't do it. Using an acetic acid sodium acetate buffer. Yes, they are partners. They are conjugate. Acetic acid, acetate, conjugate, buffer. What ratio? Let's do this quickly. What ratio of acid to base? Ratio. Okay, they ask me for a ratio. What ratio of acid to conjugate base will you need to maintain the pH at 5? You want a pH of 5. Okay, explain how you would make such a solution. They gave you the Ka for acetic acid. They ask you for the ratio. Is it buffer? Yes, it is buffer. Guess what? I have nothing else to write except for the formula for buffer. Nothing else. This is H plus equal Ka times, this is my weak acid, over weak base. Therefore, guess what? What are they asking me for? They're asking me for ratio. They are asking me for this. Okay, to make things easier, why don't I call it ratio or X? Alright, so they are just asking me for this. So that ratio equal, is that H plus over Ka? It is H plus over Ka. And guess what? They give me pH. There's no problem. I can find H plus. Is it 10 to the negative 5? Okay, this is 10 to the negative 5. It's not a big deal. Over. And then they gave me Ka. My Ka is 1.8 times 10 to the negative 5. So, what is 10 to the negative 5 divided by 1.8 times 10 to the negative 5? What is it? 5 over 9. But I need a ratio. 5 to 9? Okay, so this is 5 to 9. Can we reduce it? Okay, so how would you make that solution? We will make 5 moles of Okay, was your answer 5? What? 5 moles of acid for 9 moles of the base. Dissolve it is enough water. Okay, enough water that can dissolve it. This is your ratio. This is how you will get a pH of 5. Okay, by mixing a certain amount of that acid to a certain amount of that base. Alright, but let me quickly tell you, when I say to dissolve it with enough water, there is something we call buffer capacity. For buffer capacity, you need enough of that weak acid and the weak base to react with that strong you are adding to it. Okay, buffer capacity. Buffer capacity, you need two things. You need a good ratio of the acid and the base. The best one is 1-to-1 ratio. And then you need a concentration enough to react with that strong. Alright. Let's do, well, at least this page. At least. If it's different. A buffered solution consists of this. This is ammonia. And if you remember, it is a base. And this is ammonium. This is a conjugate acid. I don't think I need to do this. It is the same thing. All you have to be very careful about is this is ammonia is the base. Ammonium is the acid. Because I told you not to change the buffer formula, then you would have to find Ka. Can we just set it up and then even if we don't do it completely? Okay, all I have to do is write down my buffer formula. Equal my Ka times, this is weak acid, remember, over weak base. Okay, H plus equal, if you are fast we can still do it completely. Guess what? They did not give me Ka, that's okay. I know Ka equal Kw over Kb. It is 1 times 10 to the negative 14 over my Kb 1.8 times 10 to the negative 5. Don't change anything, just find your Ka. Times my weak acid is 0.4. So I have to identify the acid versus the base. It is 0.40. And then the weak base is 0.25. And the H plus is 8.89 times 10 to the negative 10. And they ask me for pH. The pH is 9.1. Thank you very much for being so fast. So we said we wouldn't do it, but we did it. Calculate the pH when 0.1 moles of gaseous HCl is added to 1 liter of the buffered solution. So once we start adding, we change to moles. We do the exact same thing, but we just change to moles. So we need to find the moles, but it says 1 liter. That means the molarity will be the same as the moles. Okay, calculate the pH when 0.1 mole of HCl is added to 1 liter. Because it is 1 liter, it is moles. The same. So all we have to do is add. Okay, this is moles, not bracket anymore. It is not bracket. Okay, because they are adding an acid, I just add that moles to the acid. It is 0.1. And then I take it away from the base. 0.1. Take away. Okay, so the first one was 9.1. And then the second one is 8.73. Okay, not bad. You are adding a strong acid. 8.73. Good job. Okay, let me see how far. Yeah. Okay. You know what? And I don't want to come back to this. Let me at least tell you what to do here. They ask you, a chemist needs a solution buffered at pH 4.3 and can choose from the following list of acids and their soluble salt. Okay? So you have acid and soluble salt. Calculate the ratio. Remember, we already did ratio. Calculate the ratio required for each system to yield a pH of 4.3. We did that. You have the pH, they ask you for the ratio. But they ask you which system works best. All you have to do, I'm not going to do this, all you have to do, find the ratio for each one of them. The ratio that is close to 1 is the best. Okay, I already told you when you have a ratio of 1, it is the best buffer. So the ratio that is closer to 1 is the best. Okay, unfortunately, we are running out of time. Even though I have a lot of more practice, I will end up asking you to do the rest of the practice on your own. So I won't have to come back to buffer. So next class, we will discuss titration. Thank you very much for your kind attention, and I hope you really practice. That's the only way you can master this unit. Okay, so enjoy your day. I'll see you next class. Bye.